Now let's go back to again encoder-decoder perspective. Here, as we know that given the graph, I want to learn a function f(inc), which is encoder function that maps each node to a lower dimensional vector z. Here, the central theme is to learn to decode information on each node, which is in a higher dimensional vector, from a lower dimensional vector. So what we are trying to do is, I am trying to go from this lower dimensional representation to certain higher dimensional representation of node. If I can learn such a encoder, then what I can actually ensure you that my lower dimensional vector space, which is basically defined by Z or set of Z's, contains all the information on each node that is represented in higher dimensional. Or the other way around, when I go from graph domain to embedded domain, I am not losing any information, or I am losing very less amount of information, and my lower dimensional representation has all the information which I need, and that makes lot of analysis straightforward as well as computational efficient. Hence, if I have that, I can perform my downstream task. If I have that particular kind of embedding, then I can perform downstream tasks using low dimensional vectors. This is similar to what we have learned in a dimensional reduction. Of course, dimensional reduction and the embedding has some difference. Here we are trying to capture the high dimensional space of a particular node in a lower dimensional. Okay. So node itself is not changing, while sometime in a dimensional reduction the variable may change, like for example PCA. We use either score or loading vectors. So now let's look at the key components of encoder-decoder perspective, which we have to actually keep repeating for a different kind of encoding methods. So first one, which I already described, is encoder function, which is finc. What it does, it generates the node embedding using a graph. So I have only provided input as a graph, and it will generate the node embedding. Formally, it is a function which takes a node from V set and generates a d-dimensional vector. Here this ZU is my embedding vector, which is again, as I told you, is a d-dimension because it is in RD. It's a real number, continuous vector, which represents a node in V. Remember, ZU is for the youth node. And the interesting part here is this finc, which is a encoder function, contains embedding parameters to be optimized during the training phase. So we have to actually get this embedding, and these embedding parameters are actually has to be optimized during the training phase, and that is the parameter of finc. Let's look at the finc of U. Can be written as Z into EU and equal to ZU. So here again, encoder function is finc, the input is node in the graph, any node in the graph which belongs to V. The EU is a one hot encoding vector for node U. And Z is a embedding matrix. Typically this will be n cross d dimension. Okay. This will be d cross n dimension, and EU is n cross 1 dimension, where you can think of this one is going to be 0 0 0 1 0 0 0. So it will have 1 where the node U is present, and then we can get the ZU, which is embedding of node U, which extracts. So this particular embedding can be extracted by defining this EU from our learning parameter Z. So Z, in certain cases it can be written as n cross d, certain cases written n cross d. Depending on that, we can choose the parameters. If we look at Z as a matrix here, it has a d rows, so these are d rows and n columns. And what we are interested in is finding out a particular column which belongs to, or take this one, is Z U. Okay. So this particular operation will allow us to extract this particular column corresponding to U. Let's look at the another component, which is a similarity function, which is SGUV. The objective of similarity function is to map the relationship between nodes in the network and embedding space. So it will actually take two nodes in V cross V and project it into R plus. It provides measures of the similarity between two nodes in the graph. So there are different measures of similarity we will discuss in the future, and that can be used to represent a number which is in a R plus. Simple example is elements of adjacency matrix can be a similarity measure. So similarity function will take each element between U and V nodes and gives us a R plus. So input here can be two nodes and V, and the output, depending on whether they are adjacent or not, it can be 0 or 1. Okay. So as I told you, each element of this one can be represented by SG. So similarity function for the nodes U and V in the graph provides us element of, in this particular element U and V of adjacency matrix A. This particular example we'll look at it when we talk about certain methods. What is the objective of decoder function? Decoder function f dash, its job is to reconstruct a user-defined graph statistics or similarity measure from embedded vectors of the graph G with V as a node set and E as a edge set. Now graph statistics can be different. Local neighborhood of the node we want to preserve, like adjacency is providing some kind of information, or other higher order information we are looking for. if we want to preserve them, we are going to use those as a graph statistics, like age between nodes or cluster of nodes or graph in general. So typically we are using pairwise decoder function, which actually takes two nodes or their embedding and try to give output which is a R plus. So look at it, when you look at the similarity function, the out is R plus, input is two nodes. In case of FDEC, we have two nodes embedding as our input, and we are getting the output which is in R plus. Usually FDEC contains no trainable parameters. So all the trainable parameters are in the embedding functions. Its job is to take those embedding and create a new graph statistics of interest. So take an example of ZU and ZV, which are two embeddings in RD for the pairs of nodes U and V, and what it will do is try to take them as an input. As we discussed, this is a function, and if you look at ZU and ZV, they are nothing but obtained from function of FINCU and FINCV. This is obtained from our encoder function, so I am putting here, and what we are interested in, that it should approximate some similarity function as GUV. And the last one is a loss function. Remember, we are interested in learning. When do we know that the learned parameters are the best parameters, or learned embedding is the best embedding? Of course, we will define what is the best now, and the best comes from the loss function. So loss function is measures the comparison of the output of decoder function with the output of our similarity function for all node pairs in the graph. Here we are looking at a pairwise comparison, and usually we will look at pairwise comparison, and it is a user defined loss or objective function. Why it's user defined? Because user will decide what information user would like to preserve from the graph to the embedding space. So this is typical user defined loss function structure. Here we have to define several things, but we'll look at the details in some time. It has all the elements of encoder-decoder perspective, and it's typically used to train the model, and that's why it is one of the important aspect of our node embedding, or in general graph embedding. And it actually measures, as I told you, is the quality of reconstructed similarities with the similarity of the graph G in general. So it's look at it, it has the reconstructed similarity versus the graph similarity. So this particular part is presented by this, and this particular part is presented by this, you can say this function. So let me look at it. What we are interested in is minimizing the reconstruction loss L over a set of training node pair D. Here loss to be minimized is L, which is basically defined like this. It is sum over all the node pair UV. So I have to look at all the pairs. Here it can be also written as E. Loss function is L, which I have to define. The estimated similarity based on the decoder function is f-dec, and the true similarity is given by SG. And we are going to minimize this function to learn our embedding. It can be here, this particular loss function can be a squared error or cross entropy loss depending on the objective and what kind of output we are interested in producing. Typically, we do not use some hands to solve this optimization problem. We have to use a standard algorithms. We use stochastic gradient descent or more generalized algorithm to solve this kind of loss function depending on what kind of loss function form is. Also, we will see that there are, when we formulate certain loss function, in certain formulation we can use matrix decomposition related techniques such as SVD, singular value decomposition, to solve the problem. And that is going to be a next part of our lecture, where we are going to discuss how different formulations or different methods varies from the formulation of loss function, SG similarity and the f-dec in general. And you will see that there is some commonality even there when it comes to decoder functions or a similarity function or even a loss function. So let me summarize. The objective here is to come up with the embedding such that the similarity between u and v in the graph is approximately similar to the reconstructed similarity using the embedding of those two nodes, which is here you can see uv transpose uv should be similar to similarity matrix. We have done it. Just note that this is one way we are defining the decoder function. It can be other decoder functions possible. And as I told you earlier, I want to define f encoder functions and train their parameters such that I achieve this optimization goal. When I achieve that, what I will have is, I will have encoding for the node u, which is here, and decoding of the node u with respect to some kind of similarity in based on local neighborhood relationships. And what I will learn is this z of u, which is the embedding of u node. So encoder function map node to the lower dimensional vector z, and decoder reconstruct graph statistics or similarity measure using the latent vector.